Greetings everyone. My name is Kashvi Singh and I'm currently a first year student at Symbiosis Institute of Technology, Pune. I'm pursuing BTech in Artificial Intelligence and Machine Learning. In this video, I'm going to tell you how I prepared this Power BI dashboard for a given data set of steel industry energy consumption and what inferences we can draw from each of these plots. To begin with, I imported the data using the get data feature and going to CSV since my file was in CSV format. And after importing, I got to find it in the right column of data. And when I click on the name of the dataset, I can see all the fields or the column names present in the dataset. Now, to analyze different trends, we first start with analyzing the energy consumption over a period of time. For this, we have days and months. I selected the data field named date, and accordingly, since I want to do the date of the month first, then I just selected the day, and I selected a chart called the column chart since I believe that it would give the best inferences. And on the y-axis, I chose usage in kilowatt hours since that represents the energy consumption in this data set. After plotting this, we get the first graph of our dashboard, which is this one. When we click on this, we can see the energy consumption on different dates of the month. For instance, on the first date of every month, the total energy consumption was around 18,000 kilowatt hours. Then maybe on the 15th day of the month, the sum of the usage was around 32,000 kilowatt hours. And by the end of the month, again on 30th it was 27,000 kilowatt hours, and on 31st it was a bit lower, that is 18,000 kilowatt hours. This column chart is an adequate representation of the trend in the dates of the month. Though, if we notice, energy consumption slowly increased in the first 8 days, then started to decrease and increase again. The month follows a similar pattern, and by the end, there is a small decrease, finally. Going back to the report, let's now analyze the usage energy consumption by month. The total energy consumption for each month is represented by this column chart. We can notice that the highest consumption was in January with 120,000 kilowatt hours. And the lowest consumption was in September with 58,000 kilowatt hours. Moving forward, now we explore more features such as the relationship between energy consumption and reactive power. So we have two factors, leading current and lagging current. So for leading current, reactive power with usage, we get this plot. What this means is, for the lowest usage, around 8 kilowatt hours, the leading current reactive power is highest, goes high and then falls down. The leading current reactive power is highest for 3.71 kilowatt hours at 2025, and after a while it just decreases to around 0. It keeps varying around 0 till 150 kilowatt hours. Now let's compare this with lagging current reactive power. If we look at this graph is a little different from the leading current reactive power with energy consumption. However, in this we can note that the peak value of reactive power goes at 2.88 kilowatt hours, though after that it keeps varying, not around zero, but somewhat between 0 to 500 for the different values of usage till 150. However, this was not the case for the leading current reactive power. Now we will analyze the relationship between leading current power factor by energy consumption. Now this graph is similar to the leading current reactive power and energy consumption. As we can see, the peak value for this again goes at 2.88 for 47,000 value of the leading current power factor. And then it goes on to decrease. It mainly varies from 2.45 kilowatt hours to 6.27 kilowatt hours. After this, the power factor keeps varying from around 0 to 100 or 150, and after a certain value at 140 kilowatt hours, the leading current power factor just stays constant at 100. Now looking at the lagging current power factor. Again, the lagging current power factor mainly varies from 2.45 kilowatt hours to around 8 kilowatt hours, and the peak value goes at 3.02 at 39,000 lagging current power factor. After it increases and then sharply decreases, we can note that the value of power factor varies from 0 to 1000 for different values in usage and energy consumption till 149. We can also look at this pie chart, which represents the percentage contribution of leading current power factor and lagging current power factor in the total energy consumption. Now we will analyze the relationship in CO2 consumption by load type and energy consumption. If we look at load type, we get the value of CO2 consumption with different types of load, that is light, medium and maximum. We can see that for light load we have the highest consumption of CO2, then lower for medium load and the lowest for maximum load. For CO2 consumption with usage, we get a similar graph, that starts its variation from 2.45 and goes till around 7. It rises steeply till a value of 2.88, and for which the CO2 consumption is 556, and then sharply decreases at 7 till 7. And after that, the value of CO2 consumption just varies from 1 to 20 for the increase in energy consumption in kilowatt hours, and after a point it just stays constant around 1 or 2. Lastly, we will see the energy consumption according to type of the weekday, whether it is a weekday or a weekend. We can see that the energy consumption is highest, that is 87.79% on weekdays and only 12.21% on weekends. Finally, we have this gauge that can act as a short conclusion, which shows the minimum energy consumption at 0 kilowatt hours and maximum as 157.18 kilowatt hours. It shows the average energy consumption is around 27.39 kilowatt hours. Through this, we can get a comprehensive analysis of different trends and relationships in the given data set of steel industry energy consumption. And we have been successful in doing so. Thank you for watching this video.